this video, we're going to talk about how to reverse the calculation that we've done in the last two. So in the last two videos, we've calculated the probability, or the percentage, or area under the curve, given some boundary values. Now, given a percentage or probability, I want to reverse engineer what boundary values bound that area under the normal curve. So generally what we want to do is we want to find the area to the left of the boundary. We're going to do that by drawing a picture, just like we did for finding probability. So we want to draw a labeled normal curve. For the table, we need to find the area to the left, and so the picture will help us do that. Once we've found the area to the left of the boundary value we're trying to find, we're going to search the middle of the z-table to find that area, and then read the z-score off. We're going to reverse engineer what we did. So I'm going to scroll back up to our z-distribution, and you can see that it's still marked up from a couple of our calculations. When I was calculating a probability, I knew my z-score was 0.40, and then I read off down to find the area. Now I'm going to look up an area and then read backwards to figure out what its z-score is. So the z-score for an area of 0.7910 would be 0.81. Sometimes, after you've found the z-scores that form the boundary, they're going to ask you for the x values, and that you have to reverse engineer. We take the formula for our z-score, and we solve it for x. We isolate x by itself. That's a two-step algebra process. I have to multiply both sides by the denominator sigma, and then I have to add on the mean to get rid of that mean. And so that moves those things over to the other side, and I end up with an expression that looks like this. Because your tests are open note, and I don't expect you to memorize, if you're asked to find a data value from the table, given a z-score, this is the way to go. Grab for this formula. If we're doing it with our calculator instead of with a data table, we're going to use a command under the distribution menu, second vars, and it's called inverse norm. Inverse normal, it's option 3. And depending on your calculator model, you may be able to do areas under the curve other than left tails. So I'm going to pull it up on my screen, and you'll see this model of calculator with this operating system gives me an option for an area in a left tail, an area in the center of the curve, or an area in the right tail. Older model calculators don't do that. So if you give this program a minute, it's going to pull up an older model. If I go second vars and I pull up inverse norm, it just gives me area and then mean and standard deviation and paste. And what that means is it will only find areas to the left. I would strongly recommend, based on my experience teaching statistics, that you rewrite all problems as if they were areas to the left of the boundary value and leave this set to the left setting. That tends to have less problems. What I've noticed in the past, particularly when we fill in a mean and standard deviation different than 0 and 1, is that the center and right probabilities don't always come out correctly. So it is safer if you leave this set to left. The nice thing is if you leave it set to left and you change the mean and standard deviation, the value that inverse norm will spit out is the data value, not the z-score, meaning you don't have to go through this extra step at the end. What I'd like to do is some examples using both methods so you can compare. There is no right or wrong. Use the method that is more comfortable for you, the data table or the calculator. So for this example, it says a personal computer is used for office work at home, research, communication, personal finances, education, entertainment, social networking, and a myriad of other things. Suppose that the average number of hours a household personal computer is used for entertainment is 2 hours per day. Assume the times for entertainment are normally distributed and the standard deviation for the times is half an hour. So they've given me a random variable x, which is hours that your PC is used for entertainment. And I'm told that that variable for x is normally distributed with a mean of 2 hours and a standard deviation of half an hour, 0.5 hours. And the first question says, find the maximum number of hours per day that the bottom quarter of households use a personal computer for entertainment. So I'm going to draw my picture. I'm going to mark, ooh, that looks a little funky. Bring that up there. I'm going to mark my mean in the center, and then 3 standard deviations out in either direction. In this case, I know my mean is 2, and I'm counting by halves, because my standard deviation is half. I'm interested in the bottom quarter percent of data. I know 68% of data sits here, leaving about 16% for the tails. So there's about 16% less than that 1 standard deviation marker. So I expect 25% is probably just a little bit above that. So I'm going to guesstimate, I'm going to mark it here. And it said bottom quarter, so that's why I'm putting the 25% here in the lower half on the left side. And bottom quarter is 25%, or 0.25. I'm looking for the x value that forms that boundary. What is the maximum number of hours that forms the boundary between the bottom corner and the upper 3/4? So I know if I'm looking for a boundary value, I'm going to call, inverse norm. And I know inverse norm is going to ask me for an area, for a mean, for a standard deviation, and for a tail, which tail is the area in. When I put the area in the calculator, I need to use the decimal form of the area, not the percentage form. So I'm going to enter the area as 0.25. My mean is 2. My standard deviation is 0.5. And my tail is left, because I shaded that picture to the left. It's a less than problem. So let's go ahead and run that calculation. Second var is option 3. Our area is 0.25. Our mean is 2. Our standard deviation is 0.5. And we get x is equal to 1.66. I'm going to round it to 2 decimal places. And specifically, this is a number of hours, 1.66 hours per day that the bottom quarter of households use a personal computer for entertainment. So the bottom quarter of PC entertainment usage, it caps out at 1.66 hours. If you look at where we marked in the table, we marked our boundary, our guesstimate, as a little bit bigger than 1.5, and that matches that prediction. So we did pretty good in guesstimating where our upper boundary was for that picture. If I wanted to do this with the data table instead, so let me scoochie this over and I'll show you the data table method. So for the data table, the first thing I'm going to do is I need to go to the data table and look for that area in the left table in the middle of the table. So 0.25. I scroll back up to this table. I know it's on the left half, values less than 50%. I'm looking for 0.25. 2.82. There we go, right here. Exact. Oh, that's 0.025. I don't want 0.025. I want 0.25. I need to go further. Got a little ahead of myself here. 451. Wait. Oh, so I see right here a 0.2514 and 2483. So my guesstimate is I'm sitting halfway between those, which would be a z-score of negative 0.6. And if I track that up, that's sitting between 7 and 8. So negative 0.675 if I had to guesstimate. Negative 0.675. So from the table, z is approximately negative 0.675. And then I'm going to use that formula to find my x value. So x is going to be my z-score, negative 0.675, times my standard deviation, 0.5, plus my mean, which is 2. So on our calculator, I have negative 0.675 times 0.5 plus 2. And you'll notice that if I round that to 2 decimal places, I also get 1.66. And if I look, that decimal that we get from the table is accurate out until the 4th decimal place, where we start to see a little bit of a difference, which is out in the 10,000ths place. So the table gives us a fairly good estimate. The calculator gives us a more accurate estimate, but both will get us to the same place. All right, so let's try another one. The next one says, find the 80th percentile for the number of hours a household personal computer is used for entertainment. So remember that 80th percentile is the data value for which 80% or less of the data values are at that value. In other words, what they're saying is that px less than x 80th is equal to 0.8, or 80%. They're telling me that in my standard normal picture, ooh, let me fix those labels real quick. Not all of it, just some of it. There we go. That in my standard normal picture, I want 80% of the data. less than my boundary value. Percentile is 80% or less than or equal to my value. So where is that 80% divider? So let's go ahead and label our curve and mark where we think that sits. Be 3.5. So I know this is 68, and I know this is right here is 16. And 68 plus 16 is 84. So sitting here at my first standard deviation on the positive side is 68 plus 16, which is 84. It's a little bit too big. Halfway point is 50. So I'm probably just a little bit less than 2.5. So I'm going to guess that my 80th percentile is sitting at about here. And I want to know what that x value is, so that this area less than x is 80% or 0.8. So we'll do our calculator first. We know inverse norm. Our area to the left of our boundary is that percentile measure, 80 or 0.8. Our mean is still 2, and our standard deviation is still half. And this problem is also a left tail question. Percentiles are always left tail questions. So on our calculator, second bar's inverse norm to find a data value, and we want 0.8. Everything else stays the same, and we get 2.42, which is exactly that region that we were predicted we were sitting in, between 2 and 2.5, closer to 2.5. That's spot on what we thought it would be. We can also do this for the data table. If I scroll back up, I know in my data table I'm looking for 0.80 in the data table, 0.80. And I see here a 0.7995 and a 0.8023. I think 0.80 is probably closer to this. So I'm going to go with this value, and that's positive 0.8, and if I scroll up, 4. So z-score of 0.84. 0.84, 0.84. So z equals 0.84. We know that our x value is our z-score, 0.84, times our standard deviation, 0.5, plus our mean. So that gives us 0.84 times 0.5 plus 2, which is exactly what we got from that table, 2.42. All right, if you have any questions on how to find boundary values given a percentage or probability, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.